Hello everyone, I'm Amogh. We're going to talk on this topic. Basically, we'll be focusing on how vector indexing is implemented. I have an overview of that. And distributed vector store like Yugabyte. Before we start, move forward, I'll just read to you a slide. So I'll just talk a bit about myself. I am part of the growth and ecosystem team at YugabyteDB. Prior to that, I have worked on a couple of distributed data systems, including Apache Geode and Snappy Data. Yugabyte is where I first got the exposure to PostgreSQL world, and so now in recent times I've started even exploring this Gen AI world, specifically related to the SQL ecosystem, and also trying to also exploring how we at YugabyteDB have been embracing this new exciting phenomena and trying and understand that. So this talk is part of that effort. So if you can see the agenda, I'll probably briefly mention pgvector because the advent of pgvector is what actually started transformed this PostgreSQL ecosystem because it enabled PostgreSQL to be a vector database for modern day AI applications, and it changed the use cases that PostgreSQL not changed, extended the use cases that PostgreSQL could be used for. I understand pgvector was already discussed in detail in probably previous or recent meetups, so I'm not talk a lot about that. I just wanted to mention it here before moving on to the vector indexing implementation in YugabyteDB. In that, again, I'm gonna give a few architectural concepts of YugabyteDB which will help us understand what we call this vector LSM abstraction. It's a layer that we have added while implementing this vector indexing in YugabyteDB. And then so just like summarize key considerations, other key considerations that help this distributed vector store scale, basically meet the scaling requirements of AI workloads. So yeah, with that, most of you might already be aware, right? It's both pgvector extension, so it's an extension that has enabled PostgreSQL, basically added this capability to the PostgreSQL database, vector similarity search, by allowing it to store very high dimensional data, or we call it vectors, into the database. And then this has enabled it in different use cases like semantic search, recommendation systems, and the more recent popular retrieval augmented generation applications. So I have good diagrams that I just mentioned. It showed how to extend, basically create an extension if it is not already installed in your courses. Yeah. Yeah, so when you enable this extension, of course you get this vector data type with n, which represents the dimension of the data. So in a 2D database, you will have two numerical representations for a given data, so that like it could go on to any number. And some of the similarity operators that this pgvector supports, I think there are more than this. So I just mentioned like three of them. This L2 distance function, cosine, and inner product. I'm not going to go in detail, just mentioning it here. And also, it comes with it indexing support with HNSW as well as IVFLAT, inverted file flag. If you see at the bottom, the select query, right? So that's where we are querying the embedding. Embedding is the vector data type we have. So we're just selecting on that value using the L2 distance function. So of course you can have other operators used there. So and it works with PostgreSQL query planner for efficient searches. What that means is basically the query planner is aware of the indexes and then the operators that are used, so it can decide the appropriate plan. Yeah, so I haven't mentioned the index part here. So probably when we go to next slide, that is what. So before I talk about the vector indexing part, I just wanted to share some architectural concepts for YugabyteDB, so that it becomes easier when we go later to understand what's happening. So Yugabyte has this layered architecture. So we have query layer as well as a storage layer. So query layer is something we, as you said, I mean, we have multiple interfaces in the query layers as extensible query layer. So we have this YSQL API which is compatible with PostgreSQL, and also a YSQL API which is compatible with Cassandra API. Essentially, the query layer is what will is the one which will be handling the query request from the user and forwarding that request to where the data is. So the storage layer is the one which actually, as the name suggests, handles the storage of data across all the nodes in the YugabyteDB cluster. So it handles all these features like auto sharding, load balancing of data, managing consistency. The storage layer is essentially a DocDB, which is a document store, and it is again built on a customized RocksDB, customized for higher performance. So it actually again RocksDB is kind of a LSM. It's not kind of, it's LSM storage engine. So we'll talk about that a bit more later. Query layer's job is, of course, once it receives the request, forward it to the appropriate data where the data resides. So whether it's a fetch or fetching some data from a particular tablet, or sending the data to particular tablet. So that is what the query layer does. Yeah. Yeah. Any questions? Yeah, please. So I'll quickly talk about like a few concepts specific to YugabyteDB. So we have in YugabyteDB cluster, you generally have two processes, like master and server. So essentially, master is just one which handles system metadata, keep tracks of all the records, tablets. I'll talk about what tablets are. This is essentially they are just partitions, the shards of the data, table data, and it also master process also is responsible for coordinating background operations, balancing of the load balancing of the tablets across all the nodes in the cluster, also initiating replication of under replicated data. So I'll talk about what is the under replicated data. It's essentially, you can have multiple copies of data in your cluster, and that is what we call replication. So if the configured replication is not made, so that's what we are saying, like initiating replication of under replicated data. T-server is the main guy who's actually hosting the data and serving the application data, right? It manages the tablets. And, essentially, any user request is actually handled by T-server, right? Whether it's write or read request. And yeah, I mean, so these are the topologically these are the two processes or services we call in yeah, talking about sharding, as I mentioned earlier, what Yugabyte does is whatever table data, whatever table you create, it splits the data into multiple shards called tablets. So if you have, let's say, a table with 100 records and you have, let's say, 4 nodes, of course, it can actually split the data in 4 shards or tablets, and each node will have a tablet. So that is how that way actually spreads the data across the entire cluster, not limited to a specific node. Yeah, and the second point is replication factor, which I mentioned earlier. Essentially, there is something when you configure, let's say, RF3 or replication factor 3, that means you have 3 copies of your data in the entire cluster. So that helps it actually, right? I mean, even if one node crashes, you still have the other nodes servicing those servicing requests on those data because they have the copy. Yeah, T-server can host one or more tablet peers. So tablet peer is like, I mean, for a given tablet, for a given shard, each copy is called a peer of that shard. So that's what we call tablet peer. So a single T-server still can host multiple tablet peers. Yeah, and then the last point is about like how do they make a raft group, right? So all the tablet, all the nodes of the T servers. Essentially, whenever I talk about nodes, it's essentially T server because those are the guys which actually hold the data. So all the T servers which hold this tablet peers form a raft group, and then they replicate the data between each other. Yeah, maybe I can explain the slide. It's a simple diagram. So it's essentially I just mentioned 3 T servers here, and I'm just showing this T1, T2, T3 are just 3 tablets for a given table. And then this is with the RF3, so you have 3 it goes to this mutable in memory vector index. So again, this vector index is calculated using the library which is plugged in. So you search or HLSW or other libraries in future. And once mutable in memory vector index reaches a certain limit, then it is actually persisted in, as a SST on the disk. On the right side, so that's a read request, so this topic query with a query vector. So again, it goes to the vector LSM. So it first looks at it looks at the in-memory buffer if that key is there. If not, it actually loads. It should check the persisted SST files. And as we saw earlier, so based on the data that is available in the index block or the filter block, it will know which file, which SST file to load. So there's load from disk and read from disk, so it can load the entire file also using I think memory mapped files based on that. It can load that data and then give it back to the return that as and again, the structure is per tablet. So the one which is at the bottom, right, the big square. So that this I mentioned T server there. Essentially, you have a vector LSM instance created backing each tablet. So you will have all this for each you will have the structure for all the tablets that are there. Any questions here?
That memtem size you mentioned, right? It will be for a certain limit. It will be mutable. After that, it will be immutable, right? So is it like default one, or can we pre-configure it from our end, the customer end? Can we do it?
So the size limit of the in-memory.
Yes. Before immutable, right? That size.
I don't know whether that's configurable. I think it should be, but yeah, I don't know for sure. Because I mean, there are so many tablets, so it makes sense. I mean, it should be there, but yeah, I don't have the exact answer for that.
Yeah, it can be configurable. What we need to do to take the proportion is you have to have more RAM. So
Yeah,
because
that
generally you go with
depends
1:4,
on
you
the
may not be
load
able to do
and
that.
other things, right?
Exactly.
Should be.
We can do that with the configuration, but there will be additional memory requirement you need to map it to. Suppose you are going like a M5 a 2x class, here you definitely have to go to like a R6 a 4x class or something. Yeah. I think you need to take this memory into consideration.
It's a conflict. Thanks, Varun. Any other question?
Hello. Yeah, so my question is like, what is the trade-off decision behind using an LSM storage engine? Because let's say if LSM is used for very fast throughput insertion, so and on top of that you are performing some kind of indexing which can be a slow process. So why not InnoDB or something normal?
InnoDB.
Like normal B plus T type of storage engine. What was the main reason behind using LSM storage engine?
Yeah, the main reason is, I mean, it works out well for both writes as well as read, not just writes, because when I say writes are helped here because of sequential writes, but if you look at the read path also, right, because of this hierarchical structures, we can quickly know. I mean, in my read path also, I can quickly know whether the data is available in the mutable in-memory vector index or on the disk or on the SSD files by looking at just the headers. I mean index block or the filter block. So it's helping me on both the what to say read as well as write paths. So I'm not sure what InnoDB architecture is, but yeah, this is something. I mean, it has been pretty much demonstrated strongly on the RocksDB, which is the backbone of document store DocDB we are using. And I think it's maybe Spanner also has this, so it's widely used. I'm not sure whether it's Spanner or something else, but yeah.
Yeah, so just like on top of that, so what type of metrics you have collected that your database was being used generally for write heavy purpose or read heavy purpose?
It's actually so it's a relational database, so it's actually both the workloads. I mean, it's yeah, maybe. I mean, it's not specific. I mean, YugabyteDB is not like. I mean, yeah, it is a distributed database. So you have all the data spread across all the nodes, and even if it is like one leader where all the writes go through, but reads can happen from anywhere. That is configurable based on what your requirement is. So, the decision to have it single write, I mean, maybe not directly related to your question, but it's like make sure that all the writes happen through a single point for the given key updates. So it helps with consistency.
Yeah, just to add, purpose-built for write amplification because RocksDB is meant for write amplification. But however, we are not denying any read request. Why? Because we have the advantage of raft, which helps us to read from the follower. So anyway, you already embedded the data, which you can still read from the follower, which will not have any sort of imbalance on your read and write ratio here, right? So you're still able to read from another node as a follower read, you can continue to that. That's why when we are doing the embedding, we are much faster. Even we did a scale testing of 100 million vectors quickly compared to the normal Postgres, where we are able to achieve that with the help of this vector LSM.
Yeah, thank you.
Any question? Okay, we can move to next. Yeah, so essentially, whatever we just discussed, this slide is just about that. Yeah, so the additional, okay. For the writes part, in the vector part of the data is returned to the what we call that abstraction vector LSM, right? So we also write unique identifier that actually helps us to find the original row when required later. And when inside vector LSM, so it's essentially the same path, right? Again, the newly added vectors are inserted into mutable in memory index, and then when that fills up, it goes to a persisted. It's persisted to a file on disk using the mechanism or the APIs of the underlying library that we are using. And again, on the read path, yeah. So there is one more point, right? On the read part, we need to look at the data from all these three layers, right? In memory as well as immutable on disk indexes, and then return that as an aggregated top K result. So talking about the top K query. So basically we need to go through all these three layers and then return the aggregated top K results there. So if you go to the next slide. So yeah, it's kind of a pictorial representation of this insert flow. I mean, you have an insert request coming in, which actually the tablet API writes to the instance DB, and when it's committed, it goes to RocksDB. And then for the vector, for the indexes, we write the vector data in the vector LSM layer, and also write the index, and then again when the limit buffer fills up, it goes to the persistent vector index, basically as a SST file. And the next slide, this is a search flow. This is a topic very basic. So you can see it's. I mean, if you look at bottom, you see pgvector in the database, the same pillars. So when a query hits, it actually asks for the data from. It needs to look at that data in IntenseDB docs as well as the vector LSM, and it actually needs to merge across all these three layers, and again at the tablet layer. So I mean, here if you see, we say it's merge top K from intense and vector LSM, and then after, so this we have to do it for all the tablets. So we have to do it all the tablets, and then we merge it across all the tablets. So this is it's kind of whenever a query happens, it can actually distribute across all the nodes in the cluster where the tablet data is there, and parallelly they'll process the query there. I mean the data, and then their top K, local top K, and then at the higher level it will be aggregated. So that's the flow. Any question before other considerations? So these are like some of the functionalities or features I probably mentioned earlier. So, questions? Yeah. So one key consideration is that collocation with main table, right? So whenever you create an index on a normal table, normal index, it may or may not be. So it will be partitioned. It may be partitioned differently than the original table, but for the vector for the table with vector data type, what we do is when a vector index is created, this is essentially partitioned on the in such a way that both vector index tablet as well as the original data tablet, they are on the same node. So what that helps us with, like those are like few points. It's fast local join. So essentially, if you want to join your join from actual data versus with your index data, so there's no need to have a cross shard lookup. Basically, if your index entry is on some different node and your actual data entry is on one node, so it avoids having this collocation, avoids this cross shard lookup. Yeah, there's efficient filter push on. We can say SQL predicates and vector search can be jointly evaluated. So because they are on the same tablet. Same with transactions. So you don't have to go across different tablet for that. And then region aware placement. So that region aware placement. So that basically you can ensure that the index data is also can be placed alongside the user or inference services. I mean the actual data you want to query in a geographically distributed use case. So where you have data across all the regions, multiple regions of geo. Again, about the tablets, so this is one more thing. As you add more nodes to cluster, or for some reason you go down the number of nodes, so the tablets are automatically rebalanced across the entire cluster, so that the load is, I mean, it doesn't affect any particular node in adversely. The second one is automatic tablet splitting, which is another helpful thing. I mean, if you add, like, if you want to scale more, right, all you need to do is, it's not about that. So if a single tablet grows too big because of lots of writes or vector indexes, so it is actually automatically split into smaller tablets, and then again it's redistributed across all the nodes in the cluster. So in a way it helps that it doesn't bottleneck any particular node where that huge tablet is. So basically it helps with the performance with that. Yeah, so this is another point, ultra resilient indexing. So why is ultra resilient, right? Because so the 2 points here is WCC filtering. So since this is all the vector writes are timestamped, so you have concurrent access is so there is a consistency even across even in case of concurrent access. So which is very crucial for analytics. For raft consistent recovery, so again, vector relation tracks the persistent. So when a crash happens, so it can read the val records, so that we know that we don't lose any data there. So this is something it is there already in YugabyteDB. So it is helping with YugabyteDB being a vector store. I think that was yeah. So essentially, apart from vector index implementation, so these are the design choices that I just wanted to go over that actually make YugabyteDB meet the scaling requirements of a vector data store, right? So just wanted to probably I should have a summary slide at the end, but yeah. So focus was in like how to talk about the vector indexing implementation, and now other design choices, as I mentioned, it makes YugabyteDB scalable and resilient vector data store. If you have, if you want to know more, you can of course join our Slack. You can ask your questions. You will also get questions there, right? Because we have all our engineers responding there. And also there is docs material where you can actually go and learn more about this architecture that I talked about, and of course there's lots of material even